All right. Yeah. Okay. So thank you everyone for coming to my talk, and thank you, Michael, for the sort of the assistance and invitation. Okay. So I'll quickly. This is work that we recently put up on arXiv titled "Cavity Magnon-Polaritons and a Cuprate Parent Compound." And the arXiv identifier is there in case you're interested. And so I'll start by thanking all of my collaborators on this project, in particular Andrey Grankin, who's a postdoc at UMD, Nicholas Poniatowski, who's a talented grad student here at Harvard, Victor Galitski at UMD, and Prineha Narang at Harvard, and Eugene Demler at Harvard ETH sort of split. And okay, so basically now I'll just walk you through. Okay, so this is possibly too long of a talk, so I'll try to go a little bit quickly, but I'll also perhaps find a convenient pause point. But the outline is basically, I'll give you motivation and a crash course in antiferromagnetism and cuprates in case you're unfamiliar. Then I'll discuss sort of the details of this cavity coupling scheme via the Phonon-Polaritons actually. And then, I'll talk about some magnon-polaritons that we sort of derive from this scheme. And then if I have time, I'll also talk about some Bimagnon coupling, which I think is very interesting and sort of promising way forward, but is always relegated to the end, and so it might get cut. And if you have any questions, just, I probably am not gonna be paying attention if you raise your hand, so just like unmute yourself. Okay, so really quickly, what the name of the game here? Well, a major quest in condensed matter physics is sort of this quest for higher TC. So here's this sort of, very well-known plot of different superconducting materials and their critical temperature versus the year that they were discovered, going all the way back to 1900 with, Kamerlingh-Onnes. And so two notable points here are these Nobel Prizes: the discovery of superconductivity, which is at, as you can see, very low temperature, and the discovery of cuprates, which is at high TC but still fairly low temperature in the 80s. And ultimately, the holy grail, arguably one holy grail of this field, is to push this from liquid, nitrogen, liquid methane temperatures up to room temperature. Unfortunately, this is not on the plot. It's all the way somewhere up here, and so we still have quite a ways to go in this quest. And so a natural starting point in sort of realizing this is to take some of the perhaps more promising compounds as a starting point to sort of jump to higher critical temperatures through sort of engineering or sort of control means. And that's what I'll sort of talk about. So that means cuprate materials. So starting with cuprates, we're going to try to okay, not in this talk, but the grand scheme is sort of to push the cuprates even higher. Okay, so just crash course now. Cuprates, in particular, this one here is YBCO. So if you look, basically all the action is going on in these copper oxide layers. You have 2 per unit cell in YBCO, and they're sort of very nice square quasi two-dimensional lattices, forming a Hubbard model with 1 orbital per site. And then this forms some antiferromagnetic order, and as you dope it, it becomes a superconductor. And here's sort of this fantastic phase diagram, which illustrates that it's actually extremely complicated, and we don't totally know what's going on everywhere. We sort of have understanding of the 0 doping point, which is nail ordered, and superconductivity emerges, and then it goes over towards conventional Fermi liquid paradigm as you sort of cross into the overdope regime, heading towards the right end of the x-axis. Okay, so sort of now, how do we believe? What's the picture here, and why are we talking about magnons in this compound, which we sort of understand well from a sort of just standard antiferromagnetic insulator perspective? So if you think back to phonon-mediated superconductivity for a moment, you can understand it as sort of this multiple scattering process where you have 2 Kramer's degenerate electrons that scatter via virtual phonon emission, and then they scatter again, and they will scatter again and again and again, and you can resum up this series of diagrams, and obtain basically the superconductivity characterized by your gap function, which is the anomalous correlation, anomalous correlator of this pair of electrons. And because of the virtual nature of your phonons at low frequencies, this actually gives you an attractive interaction in which forms a bound state. Cooper pairing occurs, and we all know the story. So there's also the potential for spin fluctuation mediated mechanism, which is conceptually kind of similar. You have two electrons. Instead of exchanging a virtual phonon, they exchange a virtual magnon and scatter and then scatter again. There's some subtleties due to the fact that, for instance, this is if it's a transverse magnon, we'll flip the spin of the electron. So, okay, and also typically there's no corresponding Migdal-Eliashberg or Migdal theorem that lets you formally neglect vertex corrections, but the basic idea is sort of similar. And this is sort of this makes sense in this picture of the phase diagram that I showed you earlier, where you have nail order at sort of insulator doping levels, and then you dope away and it melts. However, you still have strong antiferromagnetic fluctuations that will then sort of give you strong mediators for this pairing, and then you see superconductivity emerge once the sort of magnons go over into paramagnons. Okay, so quickly, just a note about optical control and why we're talking about cavities. So there's the sort of long-standing story, which probably all of you are familiar with, but basically, over the last decade or so, there's been a sort of flurry of activity in optical control of superconductors, in particular, using sort of pump probe methods. So sort of phenomenally, you have superconductors that you pump with strong terahertz radiation or higher, like mid-infrared. And then you can actually see enhancement of superconductivity following this sort of very strong impulsive quench. And so now there's just, there's a very comprehensive ongoing experimental and even more comprehensive theoretical exploration of this in various materials, cuprates. It's been extended to organic compounds such as fluorides. It's been extended from superconductivity into magnetically ordered systems or ferroelectric systems. So it's really the sort of explosion of demonstrated optical control in these systems. So why are we talking about cavities specifically? Well, this optical control is sort of demonstrated in a number of fantastic experiments, but by and large, for practical implementations, it's still strongly limited by the fact that it involves strong impulsive quenches. So you can imagine that you have a photon come in and maybe strongly modifies the fluctuations of the magnetic, the magnons in the system, and these can then enhance pairing, for instance, is one possible route towards explaining this experiment. On the other hand, this is also, blasting the system with a ton of energy, and so it will generically heat up, and this is kind of an effect that counters any benefits that you may see from pumping, like increasing coherence through pumping. And so you have to be very careful to mitigate heating effects. Recently, it's sort of been proposed that you can actually do this by using a cavity instead of a laser drive. So the idea here is that you sort of tune the Rabi oscillations of coherent photon and magnon degree of freedom, such that they exchange energy and dress the fluctuations without actually leaving equilibrium. You can, in principle, have this effect going on in equilibrium if they're coupled strongly enough. So the question now that we want to pose is, given that these magnons are believed to mediate superconductivity in these materials, can we control the magnons, using this cavity design in equilibrium? And basically, I'll give you one answer. Okay, the answer to this question, in short, if you take nothing else away from this talk, is yes. And I'll lay out a scheme. I'll say one possible scheme. We can do more if we want. Lay out one possible scheme how this may be realized. And in short, this is sort of the very broad theoretical proposal. So you take your cavity, you take your cuprate sample, which is these sort of blue layers which emphasize the copper oxide layers, and you take a terahertz resonator and you put it on top, and the electric field of this terahertz resonator will then couple to the magnons in the sample below. In a little bit more detail, this is actually sort of a more complicated process. On the left is sort of illustrating this, that you have your cavity is sort of a, a resonance in the terahertz. Your magnons are in fact a band of magnons extending all the way from the magnon, the spin wave gap in the terahertz, all the way up to, 200 MeV or so for the, cuprate bandwidth is quite large. And, somewhere in the middle, there are these phonons that will actually sort of mediate this cavity magnon coupling. And so I won't discuss the phonons, we'll sort of try to get rid of them as quickly as possible, but it is an interesting problem as well to consider the sort of cavity phonon magnon coupled dynamics. And if
John,
you,
can I interrupt you really quickly, because I was interested in this coupling mechanism. So you're saying that you don't directly consider the photon magnon coupling, but you have to go through the phonons.
Yes. Yes. So basically, there is a magnetic dipole coupling just to the radiative magnetic field of the cavity. And our reasoning, and I'll be honest, our reasoning initially was that, typically the magnetic field is always smaller. Magnetic dipole transitions are always suppressed relative to electric dipole transitions. Mm-hmm. However, and so that's why we sort of pursued this route. And however, okay, there are two issues. One is that, it may actually not be the case that it's so much smaller, especially because these resonators often have large inductances as well. So you can model them as an RLC circuit, and we looked at the C aspect of RLC, but you can also look at the L aspect of RLC, and actually this, okay, this may be promising. I haven't done a very quantitative comparison, but it may end up being of comparable size. And so I think it's worth investigating that direction as well. I mean,
I was wondering if there's also a Raman type coupling.
So there are Raman type couplings as well. Yeah, there's this loud and flurry Hamiltonian, which basically is E squared S dot S. Mm-hmm. And the reason why we didn't consider this one is just because we figured the cavity electric field amplitudes are already so small that E squared is smaller in characteristic electronic, electric field strengths than E. It's true that it's there and also is interesting to look at. And I think, okay, in the terahertz regime, it's probably, the way that you would need to look at this is actually going to an optical cavity, I think, because you want then a terahertz sideband of your Raman transition. So you need to be pushing your photons up to higher frequencies such that they have a well-resolved sideband. But this is another, okay. If you're going to do stimulated Raman, then that's, stimulated Raman cuprates has seen Magnons very well. So that's another interesting direction.
Okay, thanks.
Okay, so now crash course on antiferromagnetism, although I suspect that many of you probably know this, but in the cuprate, you have a two-dimensional square lattice, and so it's bipartite. You can form nail-ordered state, and your spins will, okay, as for reasons that I probably won't have time to go into, they lie in the plane. It's sort of an easy plane anisotropy, or more to say that the C-axis is penalized, so it's in plane nail order. Some simple Hamiltonian that describes this can be thought of as this, just in one layer. You have, nearest neighbor Heisenberg exchange and an isotropic spin exchange as well. And then if you look, this is sort of an exaggerated band of the Magnons. You have, in this system, you have one gapless mode still due to the remnant, rotation around the uniaxial anisotropy. And you also have, one gapped mode, which is sort of gapped to energies of order governed by the anisotropy. In this model, is sort of overly simplistic in certain aspects. In particular, there's no real Goldstone mode. At very low frequencies, all spin rotation symmetries are broken, and so you should expect the other Goldstone mode to get gapped as well. This is not going to be super important for our discussion, but it is also, there are more complicated models that would reflect this. Okay, so then really quickly, also, we also basically consider a bilayer cuprate system. And so you actually have stacks of these sort of two copper oxide layers per unit cell. And so in addition to the intralayer Heisenberg exchange and anisotropies, we also take into account a very sort of, this is what you would get, just what I plotted earlier, very weak interlayer coupling. This is sort of going to gap out further modes of your spin wave spectrum. And it's sort of important for stability reasons sort of technical details that I'll talk about later. But it's basically you have like one acoustic magnon per bilayer and one optical magnon bilayer, and then you have two sublattices, so you just double this. So you have 4 bands per 4 magnon bands, and 3 of them get gapped out, and 1 of them remains gapless in this approximation. Okay, so now I'll talk about the polar phonon mechanism a little bit, because that's kind of the actual details of this derivation. So what we consider is one particular polar phonon mode, this B1U mode. It corresponds to the planar oxygen's motion in the c-axis direction, and sort of all of them going in unison. So it's dipolar mode because oxygen has a charge relative to copper, and they're all moving together, so you get an oscillating dipole moment. And this therefore then couples linearly to your cavity photon, so your standard Phonon-Polariton picture. It's just this eliminating the dispersion of the phonon mode is sort of this local coupling mechanism. On the other hand, when the mode is displaced, basically, if you imagine instantaneously taking a snapshot in time of this phonon mode, you find that your copper oxygen copper bond angle is distorted away from linear, and then spin orbit coupling gives you a Jalachinsky-Moriya interaction, just because you have sort of this bent bond angle. This is sort of well known in the theory of superexchange, that if your bond is nonlinear, you'll generically get Jalachinsky-Moriya interactions. And so if we take into account this by first taking basically the electron-phonon interaction that corresponds to this, so when you have this displacement of the phonon mode, you get a basically additional spin orbit coupling hopping term that looks like it basically looks like a Rashba sort of spin orbit coupling, where the Rashba spin orbit is proportional to the phonon displacement, which follows from considerations of inversion symmetry. Then this gives you some kind of spin flip hopping between neighboring sites, in addition to the regular sort of isotropic hopping, which dominates. So this is sort of weak in comparison, but it's there. So now what we do is we just follow the same sort of downfolding procedure. We first take the electron phonon interaction, and we project out the doublons. This is at single occupancy. This is sort of very well approximated, provided you're below the sort of Hubbard band gap, and you'll get some kind of spin phonon interaction here. This is sort of what I just said, that you actually get a Jalachinsky-Moriya interaction that's proportional to the phonon displacement. This is so-called dynamical Jalachinsky-Moriya interaction, or has been previously studied in other contexts as this dynamical multiferroicity. It preserves inversion symmetry, and I'll get back to that in a bit. Actually, we go one step further just to simplify our lives by also eliminating the phonon dynamics, basically just using the equation I showed you earlier to integrate it out, and it becomes enslaved to the cavity electric field, which then directly couples the cavity electric field to the antisymmetric spin exchange, and you derive the coupling constant here is essentially the Jalachinsky-Moriya interaction per unit displacement times a typical displacement per photon of cavity field. So what that looks like is that you basically have a cavity photon come in, it displaces this phonon mode, and then this exerts a torque on the neighboring spins, and therefore you get a coupling to the Magnons through this sort of virtual phonon mode. Okay, so this is now sort of the Hamiltonian. The simplest incarnation of this Hamiltonian that we're tasked with analyzing is this just a single copper oxide layer plus this sort of cavity coupling. Just to put some rough numbers, I'm sorry, it's in picometers because I couldn't get the angstrom symbol in Keynote, but basically if you analyze, there's actually a static displacement of this phonon mode in the bilayer system that gives you sort of a way to estimate the rough spin orbit coupling size. It's approximately 45 MeV per angstrom of displacement. And then the phonon mode is at 41 terahertz. So this is sort of integrating out is valid, at least for the the Magnon band gap. Once you get up to the bulk of the Magnon spectrum, you have to treat the fully coupled system, which we don't in this work. And the oscillator strength can also be read out just from the LOTO splitting of this mode, which is sort of experimentally very well known. And you can estimate this number comes out something like 4.4 times 10 to the minus 3 MeV per angstrom of displacement. And so that, just to put a rough number, 100 kilovolts per centimeter electric field would give you about a 5% change in the DM interaction. This is kind of small, and that's mostly due to the fact that copper is not very heavy, so spin orbit coupling is not super strong. However, this is kind of countered by the fact that in an antiferromagnet, what governs, if you think about what governs, for instance, the Magnon gap, it's the square root of the bandwidth times the anisotropy. So even a 5% change in the DM interaction would correspond to a 22% change in the actual Magnon gap that it generates. So you can get away with kind of these smaller effects. But also the other mechanism that I probably won't have time to get into actually is actually stronger than this. And so if you would like to, okay, we can also discuss that mechanism later. It's interesting as well. Okay. So yeah, now what we do is we basically just calculate the linear response, treating this is basically, the Hamiltonian that governs the dielectric polarization. You just read off the term linearly coupling to the electric field. In this case, it's this sort of spin chirality term. And so this tells you that there's a term, okay, you can just apply basic linear response methods to obtain essentially the dielectric susceptibility by, integrating out, by solving the coupled just linear equations of motion. In this case, it'll end up being linear. And so you can solve them easily. And you'll find a contribution to the, ZZ component of the dielectric tensor, which looks something like this. I won't, focus too much on the actual details. Suffice it to say, just at long wavelengths, it takes a form like this. And so there's an oscillator strength that you can calculate that involves, for instance, this sort of magneto-electric coupling constant, and the sort of oscillator strengths and the bandwidth. And it comes out to be, okay, the number is not super important. It's not actually the most important part of the story. It also has a resonance that follows the Magnon dispersion relation, which is to be expected because, the dielectric, the contribution to the polarizability is coming from the Magnon. So at resonance, it's most strong. And the oscillator strength also acquires basically a form factor that goes as q dot n squared. So it's the component of the momentum along the nail order. This understood again as a consequence of the overall inversion symmetry of the system that you have the electric field as a dipole, and the magnetic sort of magnons are, okay, they're not electric anything pole. They're magnetic dipoles, so they're even under inversion symmetry, so the matrix element has to be odd. And the only object to make this work is the momentum, which is also odd. So you end up getting this sort of q squared effective oscillator strength. Okay, so now basically we'll analyze basically this dielectric contribution, which amounts to looking for these polaritons, or the collective modes. So here's what I just showed you is the dielectric tensor, or in particular the contribution due to the magnons that we derive from the intermediate phonon coupling. And this is basically just the imaginary part of that, which tells you sort of the oscillator strength and where it is in frequency and momentum space. You see that it follows the dispersion relation nicely. It has a nice large oscillator strength, except as p goes to 0. Sorry, actually this should be q. As q goes to 0, the oscillator strength dies out. That's a manifestation of this q squared selection rule, basically, which is kind of a pain. And so we do find linear coupling of the electric field to the magnons, and it does have resonance in the Terahertz regime, which says that, in principle, Terahertz cavities are what we should be looking at. Unfortunately, there's no dipole coupling at long wavelengths, which motivates the need for sort of near field optical or momentum resolved Terahertz optics, which is okay, is pushing the boundaries, but is sort of has seen promising developments recently. Okay, so then I'll basically walk you through how we sort of go around this obstacle although I should say that it's also fairly interesting, and it, may also help provide a signature for its identification in experiment. If you could see this sort of scaling of the oscillator strength. Okay, so just sort of crash course on these terahertz resonators. Here's sort of a schematic pulled out from a paper on these split ring resonators. Essentially, they act sort of like RLC circuits. You have, resistance and inductance from the metal loop, and then there's a split in this ring that gives you a capacitive gap that's essentially some parallel plates, and your electric field is very strong. Within the middle of this gap, you have a lot of sort of electromotive force that is confined to a very small area. And so that gives you this sort of large electric field enhancements, which are needed in order to see these sort of strong coupling effects. So that's just sort of now depicted here. We just imagine putting one right on top of the cuprate. And the way that the coupling will manifest is essentially a change in the dielectric constant. If you recall, the capacitance of a medium is, governed by the longitudinal dielectric constant. And so we have to think about what happens when you start changing the effective capacitance of this, RLC circuit. So here's just sort of your standard RLC circuit. And then you imagine putting a material in the capacitive gap that has a dielectric constant, which depends strongly on frequency. This means your, your capacitance will depend on frequency now. So essentially you're just modifying the equations of motion. They still take a simple form in the frequency domain, which is where we'll be working. And so we assume that, the inductance and resistance sort of remain as they were. Okay, so where does this come from? You need to sort of use these near field methods in order to actually couple capacitively the resonator to the substrate. So here's sort of a schematic depiction. This is the sort of two parallel plates of the split ring resonator, which is sort of highlighted on the left. And your cavity electric field just sort of goes, between them in the limit where these plates are much larger than the separation. It's homogeneous, and so there's no momentum with which you can sort of overcome the selection rule. So, okay, there are many, potential ways of varying, practicality around this. For instance, there's fringing fields always just from the finite size of the plates. This is kind of messy to consider, but it's there in a real system. Instead, we sort of consider a way inspired by these scanning near field optical microscopy methods, or SNOME, where they basically use a very small metal polarizable object exposed to AC radiation to essentially focus the far field radiation down to a very sub-wavelength regime. The way that we model this is just putting sort of a metal sphere inside of the two parallel plates. The sphere has some sort of finite extent and therefore will generate, a spatially varying electric field. Essentially, the electric field of the cavity induces a polarization in the sphere, which then radiates sort of a dipole. It acts as a radiating dipole, and therefore will generate, 1 over r cubed, sort of oscillating electric field. And then you can sort of work out the geometry and take the Fourier transform to get the momentum dependence of this profile. It's messy, so if you're interested in the details, you should see the appendix of our paper. But basically, what you'll get is some finite momentum is sampled, by the electric field mode of the system, and that's controlled by the geometry of the sphere and of its sort of depth with respect to the copper oxide layers below. And okay, so the point is that this will then probe some finite gradients of the electric field as well. And you can sort of follow through on the derivation of the capacitance. And okay, again, I'll try not to like bore you with all the electrostatic geometry. We worked out, basically you get some relative contribution to the capacitance. So you have the bare capacitance from just the geometric arrangement of the objects, and then the contribution from specifically the magnons below comes in through this function K, which is essentially the fractional change in dielectric constant that the resonator on top sees. And in particular, you get some geometric factors, which are, related to the size of the cavity, effective mode volume, the thickness of the sample, the lattice constant. Important part is the Magnon contribution from the dielectric constant, or in particular dielectric susceptibility chi, momentum resolved. Now, because it's momentum resolved, we're not getting a trivial result. And the near field intensity, basically sample, how the momentum is sampled for this particular geometry. If you look at sort of the Fourier transform, it's peaked at some finite momentum, which is controlled by this parameter d, which is essentially the distance between the oscillating dipole and the sort of sample. And so increasing or decreasing d controls the relevant momentum that's sampled. The function actually looks like the one plotted on the right. So you can kind of see how this is now sampling the sort of finite momentum. And if you just put in the parameters that we derived earlier, you'll get some kind of response function that looks like this. So it's some very weird resonance, but it is a resonance nonetheless. And it's peaked around the Magnon band gap, which is sort of controlled by the anisotropy parameters, as well as the bandwidth. And also you have to be careful about the momentum that you sample. You don't want it to be too big, or else you'll have broadening by the Magnon dispersion. But if you then put it into sort of the cavity spectral function, the cavity spectral function, assuming this sort of this damped oscillator with a frequency dependent capacitance, and you find actually that there's kind of a nice avoided crossing at the point where the cavity frequency crosses the Magnon band gap. So on the right is a plot of this sort of spectral function. And on the x-axis is the sort of bare cavity frequency. So you imagine that you can sort of continuously tune the bare resonance of this cavity. And on the left is sort of just the frequency that you probe the spectral function at. And so as you tune the bare frequency across the Magnon resonance, you see that there's an avoided crossing, and your spectral function develops this like two peaks that are split by the hybridization before it sort of proceeds onwards as you move through this resonance, up to higher frequencies. So that is to say that, if you are very careful about the geometry of the system and overcoming this near field sort of obstacle, you may actually see signatures of strong coupling to the Magnons in your sample below. And that would therefore constitute the first step in essentially, coherent control of these Magnons, which becomes especially interesting when you then start talking about superconductivity or fluctuating magnetism, or stripe orders, charge orders, et cetera, et cetera. So this is actually, we think a feasible route towards controlling the strongly correlated system. Okay, I'll give you one sort of detail is that was all for a monolayer cuprate system, which is sort of overly simplified.
Can I ask a quick question, Jonathan?
Yeah, please.
Can you hear me well because I'm on mobile?
Yes,
or?
Yes.
Okay,
yes.
Great. So you showed all these works in the beginning of people coupling classical light to superconductors to increase TC. Did they also couple the light to the Magnons, let's say, by a similar mechanism that you show, or was this completely different?
There are some. Okay, I'll say that there are a few most works so far have been on electron phonon coupling. There has been electron magnon, but I'm not sure in the context of magnon-mediated pairing. There have been a few papers, which I don't have references in this talk, but you can find them in the paper. And typically, actually, I'm not always sure it's clear in those those cases. Okay, there's been some talk of Floquet engineering, which is another third option, essentially coupling to the charge currents of the localized electrons can, give you a coupling in principle to the magnons, which is essentially, downfolding to low energies. You find that these electrons become the magnons when they become localized. And so you can talk about Floquet coupling via the Peierls coupling there, which has also been discussed, but I think that's probably the least plausible mechanism, just because, okay, it requires very strong drives, which will heat intensely, and also high frequencies, but also at higher frequencies, the absorption channels start to set in. In particular, you can have like double-ons if you go to too high frequencies. And so the bare sort of Floquet mechanism doesn't seem so promising to me, at least, but okay, you know,
okay, I see.
It's all very challenging. So as far, yeah, okay, if you want like a little bit more comprehensive, then I unfortunately have to refer you to the paper. But,
okay, yeah, but I
obviously
understand. I guess also
author,
many of the, yeah, I guess many of the experimental works, maybe it's also not completely clarified what was the coupling mechanism.
Exactly.
So yeah,
well,
that's
yeah,
true.
Even, yeah, it can be in practice hard to, especially in experiment, hard to actually separate what mechanism is responsible.
Yeah.
So yeah, it's a good question.
Okay, I see. Thank you.
Okay. Yeah. Okay, so basically just this one complication is that in the bilayer system, you have okay, there's essentially a Rauch-bus spin orbit coupling, which is the origin of these anisotropies, which we actually took into account in our model. The way that it works is that you have two layers that are related to each other through sort of inversion, through a mirror plane lying between them. And so each plane in the YBCO, for instance, has a Rauch-bus spin orbit coupling, but it's opposite between the two planes, such that overall there's no sort of inversion symmetry breaking. And this was investigated actually a long time ago in the 90s in the context of YBCO. And so if you do this, which we sort of do all of the details of this, tracking through the spin orbit coupling, you get a much more complicated model, which in principle will remove all of the Goldstone modes, and also gives you the sort of microscopic derivation of the DM and anisotropy tensors. This is just illustrating that it comes from some kind of inversion symmetry, inversion symmetry acting non-trivially on each layer, so you get some kind of Rauch-bus texture. And if then follow through you get now 4 bands per unit. You have 4 Magnons bands, and okay, this is sort of zooming in at the gamma point. You see that okay, 3 of them are gapped, and then 1 of them should be gapped. Approximation is, and then if you just repeat basically everything that I told you about the dielectric susceptibility, near field, cavity coupling, etc. You can repeat it for this, which we do. And there's one new complication, which is now, it's not isotropic with respect to the orientation of the nail order anymore, which could be a potentially interesting effect that helps you, for instance, identify, in some experiment, what you're actually seeing is if you can somehow separate the momentum dependence from the crystallographic axis and also the nail order orientation. What I'm showing on the right is just essentially this dielectric susceptibility, the imaginary part, momentum resolved as a function of the angle of the nail order, looking just exclusively along momentum along the A axis. This is just, I don't want to focus on this too much, just to illustrate that it, it's no longer isotropic, and it does depend on these orientations. And so, however, the overall story is not really qualitatively changed. Quantitatively, it may change. Here, for instance, the frequency of the Magnon, band gap calculated in this model increased, but also the avoided crossing seems to get a little bit smaller for this particular parameters. But overall, the story is still qualitatively the same. Okay, we don't look into this in too much more detail, but I believe that this orientation effect with respect to the nail order could potentially be some kind of interesting effect to look for in an experiment. Okay, I guess I have maybe 10 minutes to go through the very last piece of this, which I think is very interesting. So I apologize if I'm sort of rambling, but Okay, so returning to this bilayer structure, essentially the origin of this Rashba spin-orbit coupling is that, you have a different ion lying between the two copper oxide layers and sort of outside, and this creates a gradient of the crystal field, which buckles the oxygens actually a little bit. So they're not lying exactly in plane with the copper ions, but they're pulled in slightly, and that's sort of illustrated here in this buckled, it's called this like buckling deformation. The magnitude is small, it's about 0.22 angstroms, but it's sort of definitely there, and it's the origin of essentially this like Rashba effect that, on one layer they're pulled up and you get one chirality, and on one layer they're pulled down and you get the opposite chirality. And this is, for each unit cell, and you have a stacking of these along the c-axis. And it was pointed out actually a while ago as well that in the presence of this buckling distortion, you could actually get a linear coupling to the phonon mode that's associated, that I discussed earlier, that's associated to this sort of c-axis vibration, just because the bond angle to begin with is deformed. And so if you imagine that for a linear bond angle, it should go quadratically as sort of the displacement, just by sort of inversion symmetry, it can't go linearly. But when it's buckled, it can go linearly. You're sort of, linearly varying the deformation that's there. And so there should in principle be a linear phonon, a linear coupling, even without spin orbit interactions in the system when it's in the bilayer realization and has this sort of buckled mechanism. So what does this look like? Basically, you imagine in equilibrium, okay, the gray is illustrating the copper ions and the pink is illustrating the oxygen. So in equilibrium, they're displaced from sort of lying in the copper oxide plane. And then this phonon mode, which is associated to the motion of these oxygens in unison, is activated and you get oscillation. And the phonon, the oxygens, as I said, move in unison. What you'll see, and this is obviously very exaggerated, what you see is that one, comes closer to linear and the other one gets further from linear. And so this is the origin essentially of the linear coupling. Basically, if you look at the effective copper-copper hopping through essentially the oxygens, you get at second order some sort of, you can integrate out the virtual, the virtual charge transfer, and you get, the hybridization between the copper D and the oxygen P bands squared over just the energy cost. And by essentially the Slater-Koster rules, this TPD goes as the sigma bonding times cosine theta plus the pi bonding times sine theta. And in a linear bond, theta is 0, and so you only get sigma bonding. In the distorted bond, and therefore you can only sort of vary this, you expand cosine theta for small theta, it goes as q theta squared, and theta goes as q, the small angle limit, and so you can only get quadratic coupling. However, if theta to begin with is non-zero, you'll get you can get this linear coupling through essentially the trade-off between the sigma and pi bonds. Okay, this is probably too detailed, but I just want to make sure that everyone believes me. And we actually dug into a little bit just in some of the literature. We didn't, do a thorough calculation that would be reserved for future work, but digging into the literature a little bit, it actually seems like this coupling, which we call alpha, is much larger than the spin orbit mechanism by a factor of almost 2 orders of magnitude, mostly due to the fact that copper has small spin orbit coupling. And the distortion is actually, 2.22 angstroms is not super small. So basically this says that there's another mechanism that couples linearly to the phonon that's actually much stronger than spin orbit coupling. And so it should definitely dominate. So why didn't we consider this at the outset? And the reason is essentially that if you then follow through the downfolding of this electron phonon interaction, which, exerts a torque in the bilayer system, project out the double-ons, you get some interaction like this, and then you project out the, virtual phonons, and you get this magneto-electric coupling again. The point is that it couples, there's no spin orbit, and so it has to couple to the scalar spin exchange. And so therefore, you actually can't couple to magnons linearly. And so you can't form magnon-polaritons in the conventional sense because of, this preserved spin rotation symmetry. And so it can't flip a spin and therefore produce a single magnon. It can, however, produce pairs of magnons, which are basically this Bimagnon coupling, just the Holstein-Primakov expansion of S dot S. And that will couple linearly to the phonons, and the coupling constant we estimate to be fairly strong. Okay, so just to summarize, in the bilayer systems, which you can think of in the simplest incarnation as this easy plane anisotropy plus the Heisenberg plus the interlayer coupling, which is necessary for technical reasons to actually make sure this isn't a trivial term, plus this sort of magnetoelectric coupling. And the coupling constant is actually fairly strong. Okay, this is the form it takes. So it's fairly strong, and it, inversion symmetry doesn't force this one to vanish at long wavelengths, which is great. We don't have to worry about this near field junk. Okay, not junk, I'm sorry, it's very interesting. The near field, it's a complication though. The near field complications. However, it's only working in bilayer systems, and it only produces, therefore it only produces a nonlinear coupling in the absence of spin orbit interactions. And so, you can't really find polaritons with this. Just to quickly summarize though, we looked at the calculation anyways. Essentially, Holstein-Primakov expansion gives you diagrams of this form. Basically, a photon can come in and create a pair. It can, create a pair of flipped spins, or it can scatter, a spin from one momentum, a flipped spin. It can scatter it to a different momentum. And just evaluating these Feynman diagrams, at zero temperature, gives you a contribution to the dielectric susceptibility that looks something like this. This is your sort of standard RPA procedure. Again, if you want the details, please see the paper. Basically, okay, there's an interesting effect that comes when the interplay of anisotropy and interlayer couplings. When you have finite anisotropy, you actually find an enhanced coupling to the Bimagnon continuum as well. In addition to the large coupling constant, you also essentially couple to a Van Hoff singularity because you have two-dimensional bands that are gapped. And so there's sort of a logarithmic singularity in the density of in the imaginary part of the susceptibility. I'm running out of time, but that's just sort of the spike that you see in this chi-ZZ. Basically what happens is that you can come in with a photon, create a pair of magnons. One of the possibilities has a soft Goldstone mode, and so that will not give you this enhancement. On the other hand, you can couple and create a pair in two gapped bands, and that will give you this this Van Hoff singularity. Just to see that, you just look at this momentum space integral in 2 dimensions. You can do the integration in spherical coordinates, and you'll find a logarithmic function for the imaginary part. Okay, so what does that look like? On the left is when anisotropy is 0, and then this sort of the bands become gapless, and this effect goes away. And you see that once you cross the Bimagnon continuum with this is the cavity spectral function again. Once you cross the Bimagnon continuum, you essentially just dissolve. It becomes extremely overdamped, and you don't see anything sort of interesting. On the other hand, when the anisotropy is finite, you actually do see something kind of interesting. It's still, as the cavity frequency crosses the Bimagnon continuum, okay, it first of all does become very heavily damped, which is to be expected. However, the sort of strong coupling and Van Hoff singularity are sort of conspiring to also give you a very strong sort of reactive coupling. And this this looks like some kind of almost avoided crossing, that your line shape is starting to repel from this Bimagnon crossing. There's some possible splitting above, but it's just, the damping is so strong and asymmetric that it's really not what I would call strong coupling in the conventional sense, but it is doing something interesting. And that's just illustrated here in more detail by looking at line cuts across, basically constant cavity frequency as a function of probe frequency. And you see, below the Bimagnon, if you tune the cavity to lie below, you'll see a strong resonance at the cavity, and then maybe a shoulder resonance at the Bimagnon. If you tune it to be, at higher frequencies, you set your cavity frequency higher, you see it really just gets this sort of very asymmetric broadening, which is what we saw in the sort of previous plot where it was, okay, so this is interesting, but okay. And it does signify that they're very strongly coupled systems, but perhaps not in the right way. It's not a coherent coupling, at least, on the lower plot. On the upper plot, there may be something interesting to say, especially like in an experiment, if you can identify some kind of Fano or other, interesting line shape that you get that may also help you positively identify this as a Bimagnon signature. But I know I'm out of time, so I'll just thank you for your attention. And then if you have any questions, you can always obviously reach out to me, or look at this, the paper that we posted. Here's the archive identifier, and yeah, so thank you. And I guess just take some questions if you have any. I'll stay on for like a few 5 to 10 minutes, or you can just leave if you. Yeah. Okay. So, and if you have a question, just unmute and ask it, because Mikhail left.
Can you briefly tell? There was just at the end you had this susceptibility slide, and there was splitting into two. Yeah. And there was splitting, and the initial one was at px equal to 0. No, maybe not this. Like there were two arrows like this from 0, px equal to 0. Yeah, here, and then there were two. Yeah, like this. So my question is, what is this object with px equal to 0?
Yeah. So okay, this is a good question. Basically, as I said, okay, at 0 temperature, so first of all, at 0 temperature, there are no existing magnons to scatter. So this is all basically pair, pair emission processes. The photon comes in, and due to selection rules, it excites, two magnons of opposite parity, sublattice parity, basically. And so those are the red and blue. And there's 4 bands, so there's 2 ways to do this. And one of the ways is essentially involves a Goldstone mode or pseudo Goldstone mode. So I should say that this we basically just use a simplified easy plane model for this, and so it does have a true symmetry that gives a Goldstone mode. In a more realistic treatment, there are other anisotropies that will break this and remove the Goldstone mode, so this may not be a relevant consideration in practice, but in our model, there's a Goldstone mode. And so when you produce a pair of magnons in this channel, as you saw and asked about, one of them is a Goldstone mode and can become essentially soft as p goes to 0. And so therefore it is a bimagnon, but it's like one gapped magnon plus one soft magnon. And so, okay, it would be interesting to work out, for instance, this probably has different phase space and constraints that we didn't really consider. We actually think it's sort of the less interesting one, because if you work out what is the energy of this sort of magnon plus Goldstone mode as the total momentum is 0, but as the relative momentum goes to 0, you'll find that the energy obviously goes linearly in momentum because it's some constant plus a Goldstone mode that's linear in momentum. And so in 2 dimensions, a mode that disperses linearly in momentum doesn't have a Van Hoff singularity, or not a pronounced one at least. And so this one doesn't pick up, because the mode is soft, it doesn't pick up on that. And so it kind of, actually, if you look in the previous slide, this one, when anisotropy is 0, you have 2 Goldstone modes. And so both cases give you this. And you see there is some kind of effect when you basically cross the single magnon threshold, because you get single magnon plus soft Goldstone mode, but it's kind of weak. Whereas if you have this gapping of the Goldstone mode, you get a pronounced effect at the 2 gapped mode frequency, and that's because unlike this one, this channel here has dispersion of the total pair that goes as constant plus p squared for small p, because they both disperse quadratically. And so therefore it picks up on the Van Hoff singularity. And so this mode, okay, in our model at least, is kind of the uninteresting one. This one actually gives you this strong coupling through this argument. Okay, did that answer your question? I hope.
Yeah. Kind of it's okay. It's okay. Thank you.
Yeah, thanks for the question.
I would also have another question. I'm not sure if this is obvious, but in the beginning you said that you will show how you can control the superconductivity of the cuprates, and now you've shown that you can influence the Magnons, but is it clear what they then do on the superconductivity?
Yeah, so I mean, that's a good question. That's basically the motivate. I mean, no. The motivation, that's basically the motivation for why we looked at this in the first place is, ultimately we would like to answer your question, but as a precursor, it actually was not even clear how to couple to the Magnons in the first place. So, okay, I'm hoping that now we've answered that and we can sort of start proceeding onwards. Hopefully, in another year, maybe I can answer your question.
Okay, I will ask it then.
Yeah, but I mean, it's a good question. I think there still needs to be a little bit more that's looked at in terms of, for instance, going to higher frequencies. I suspect that, a realistic idea of the pairing involves paramagnons. So first we have to generalize the fluctuation effects, and also involves paramagnons of multiple momenta, because pairing is sort of occurring in real space. And so it's magnons of short and long wavelengths and everywhere in between. And we've sort of shown how to address the sort of bottom of the band, which is right where in the terahertz. Actually, it's also an open question at higher momenta, higher energies, how much of what I've told you today carries over. So I expect it's actually fairly complicated and may take a long time to answer your question. But I think, I think it's a very good question to ask.
And maybe a follow-up question. So, I mean, now for the superconducting pairing, you consider, of course, this Magnon-Magnon interaction. I remember when I used to be a student, I also studied strong correlated electrons and super high temperature superconductors, and there was an endless debate about what is now the mechanism. So many people said, it's the antiferromagnetic fluctuations, but there were completely different theories saying, no, it's the charge fluctuations, for example. Now, could you go with your theory and maybe say, okay, if it is magnon-magnon and you put it in or if it is magnon-mediated, you put it in a cavity, this will give this or that effect, whatever it is in the end. And then if one measures this would say, so it will be probably it would be a prediction to, let's say, rule out other coupling or other mechanisms for the superconductivity. Would this be possible maybe?
Yeah, so I think that's also very interesting. And it's a good point because, obviously there's a lot of debate about the nature of the pairing interaction, and any kind of tool that you can use to settle that debate would be invaluable. Now, in principle, I've also thought about this. I think it's like, an interesting question. In practice, I think it's limited by the fact that you have to first be very sort of systematic in your understanding of your predictions in any particular theory. So I can go out and say, so you first need to understand the Magnon sort of cavity aspect very well, and sort of very clearly identify signatures that predicts and verify that theory, move on to the next step of introducing superconductivity, understanding how every single, like otherwise someone can just say, oh, well, no, because you missed a vertex correction in your own theory. And if you included that, you would have gotten the right answer. And so, so it is like a very tricky matter in practice doing that. But I think it kind of, if there's some clear signature, then that could be feasible.
I understand. So basically, if you don't see the prediction, and maybe people will say, but you've just not perfectly understood the Magnon cavity coupling, so that's why you don't see it.
Yeah, exactly.
I see.
Yeah,
that's true. Okay, thank you.
Thanks for the questions. Yeah, these are very interesting. Okay, any other questions? I guess, last call. Okay. All right, well then I'll stop sharing. Thank you everyone for coming and for sticking around, even though there were technical difficulties, and then it was also very long. And again, if you have any questions, you can check out the paper, or you can email me. Just identify yourself, so I don't think it's spam. Okay, thank you. All right.
Yeah, thank you.
Thanks a lot for the talk.